and then, yeah, we'll just get started, all right? So today's workshop is on torsion, right? And then this is the second last topic, it's the second last week. There's 2 more topics in week 10, but you're on the home stretch. This week, really easy. Next week's gonna be really easy as well. Yeah, I'll show you the layout of what's left, right? So today we're gonna be focused on torsion, and then next week we're gonna be doing theories of failure and talking about buckling too. These last 3 topics, super easy. I'm not just saying that. I genuinely think, like, if you could do bending, if you can do deflection, and you can do shear, you will be completely fine, okay? I don't even think this workshop today is going to take an hour, right? Maybe we'll finish in 1 hour or so, right? Okay. So I want to introduce to you guys what the idea of torsion is, right? Because you might have heard this word talked about, no pun intended, talked about before, okay? So if I have a beam like this, okay? Let's just say this longest dimension is L, okay? Let's pretend this is a beam, but it could be a rod, it could be any basically one-dimensional kind of shape where one dimension is a lot larger than the other two, okay? And then this is a cross-section, for example. So these are your transverse directions. I think I briefly talked about this last week. Okay, so this is your cross-section. So the idea is, for this beam, we can basically draw this line that runs through it, and we call this the longitudinal axis, or the axial direction. Let's call it axial direction. Okay. And if I have a normal beam, let's just say like this one, and there's some kind of moment that's applied this way, okay? It induces a bending moment, so it causes the beam to basically sag and have this curvature, right, which is what we were talking about in week 5 and week 7. But what happens if I instead do this? It's basically, I'm applying a moment, but it's a torsional moment now. So that's called torque, right? See what I'm saying from earlier? When I said yeah, torque. I'm going to talk about this. Okay, so torque is a torsional moment, right? So there's 2 types of moments, essentially, right? You have bending, and you have torsion, okay? So, so like, for example, if I have a wrench, and I'm tightening a nut, right? I'm basically applying a torsional moment or a torque, right? If I apply point load, and then that's your lever arm, right? That's the idea of torque, right? T is equal to P times L. So this is a torsion that's induced by a force, like a point load, okay? But you can also just apply point torsion moments, right, at some given point, right? Okay, does that make sense? Yeah? Okay, so that's what torque is. In the context of what we're doing, I'm going to show you a rod, and it's cantilevered against a wall. So it just looks like this, right? And we're going to look at circular cross sections, right? So we're just going to call it a rod that's attached to a wall and it's fixed, okay? So, this is the first equation that you have to worry about. There's only 2 equations today, okay? There's the relationship between shear stress and torque, and there's going to be twisting, a relationship between twist and torque as well, which you'll see later. So if you recall, for bending, right? So if I have a beam, you're going to see a lot of comparisons to bending, basically, right? If I have a beam and it's simply supported and it has the uniform distributed load on it, the stress distribution looks like this, right? Where the top is in compression and the bottom's in tension. Okay, so if I was to draw that a bit bigger, like this, you can actually figure that out, right? As we mentioned in week 5. So this is elastic bending. So that is basically sigma is my hat on I. And yeah, you can basically figure out this bending stress distribution where this is the neutral axis, right? If the moment we care about is the maximum moment at the middle of the beam, that's where you get M from. I is from the cross section. So if that's like a square, for example, you can figure out the geometric properties to get I. And now y hat is mapped against your depth, right? So the further away, the further away you get from the neutral axis, the more axial stress you have, right? So this is how the correlation between axial stress and bending works. Okay, does that make sense? So this is from week 5. So I want to draw your attention to this because the similarities with the shear stress and the torque, right? One sec. So looking at this formula for torque, instead of axial stress, we have shear stress, okay? And then instead of moment, we have torque. I'm kind of doing this weirdly. I'm going to circle this one and put an arrow here, okay? And then instead of moment of inertia, we care about the polar moment of inertia. Fuck, I did the same thing. I'm going to circle this one and I'll point this one here, okay? Do you get what I'm saying? So there's analogies everywhere, okay? The other thing is that y hat, which used to map how far away you are from the neutral axis, right? Now y hat becomes rho, and rho is your radial distance that you care about, okay? So if you look at this diagram that I've drawn, the idea is that your shear stress is a linear curve if it's elastic, and it's the highest at the point furthest away from the middle, okay? So it's a good example. So if you imagine my arm, right? If you imagine my arm and I'm twisting, I don't know if I'm even allowed to say this on camera, right? But I don't know if like in high school you heard what like an Indian burn is or whatever, but it's where you do that to your hand or someone you want to like hurt, I guess. I don't know. You're doing that. You're basically applying a torque to the arm, and then the point that's like the skin, right, is furthest away from the middle, and it experiences the most shear stress. Okay? Does that make sense? That's the weirdest analogy I've ever done, right? Okay? But if you do this with your arm right now, right, you're applying a torque to it, and your skin is the part that experiences the most shear stress, right? Okay? That's basically what this formula is saying. You're mapping the amount of shear stress. I'm really sorry about that. I don't know what that was. That was a weird analogy. Okay, but like, yeah, okay, that's my arm, right? The skin's the outer part, right? So it experiences the most shear stress, right, when you apply a torque to it. Okay? But I can map that versus rho. So rho is the equivalent of y, okay, from the other formula. Okay? So rho is how far away am I from the middle. So at rho equals 0, that's where you don't have any shear stress. Okay? But if at the outer edge, that's rho is equal to c. So what's c? C is the same thing as the radius, the outer radius, but in this particular topic, we call it c as the max radius, okay? That's just a notation thing. Okay? All right. I'm going to show you how to calculate the polar moment of inertia because, like, yeah, we're familiar with the area moment of inertia, which is I, but I'm going to show you what J is all about. Okay, so J looks very similar to the formula for. So this is BD cubed on 12 is the moment of inertia for a square. I forgot the exact one for a circle, but if you look at the circle one, it's going to have something like pi 2 something something, whatever, right? So there's going to be an equivalent for I, but for a circle, and it's going to look very similar. What I want you to know is that in this course, there's only going to be 2 types of cross sections that you're going to need to calculate J for, okay? You're going to need to calculate for a circle, which is a solid rod. Okay, so if that's a cylinder, that's a solid rod, right? And a hollow one, like that, okay? So it's hollow on the inside. And the only difference in notation is CO refers to the distance from the middle to the outer edge, and then CI refers to distance from the middle to the inner edge, okay, of the hollowness of that cylinder, yeah? Okay, but for other shapes that aren't circular, it's actually very hard to calculate, and there's only approximate formulas for it. So it's not going to be in this course because it's not really like fundamental like solid mechanics, which is kind of what this course is about. It becomes more of like engineering approximations kind of thing. So yeah, like there are formulas which get you pretty close to what the real number is for the polar moment of inertia for like an I-beam, which will be in steels if you guys are doing steel structures next year or whatever. But it's not going to be covered in this course. So this will be in the standards for steel, etc. But you're not going to deal with any other shapes other than these 2, okay? Okay, the other thing is angular twist. So going back to my analogy with bending, right? If you have, again, simply supported beam, you have a simply supported beam, and it deflects some amount like this, okay? You know what? I'm going to draw just it one-dimensionally. That amount of deflection, right? There's formulas to calculate it, which we covered in week 7, but that's vertical deflection, right? That's like how much it physically moves up and down. But for twist, right? Twisting is basically rotational displacement, right? Okay, and I know I just said you're only going to deal with circular cross sections, but just for the sake of showing you guys like how this looks, I'm going to draw it as a square cross section because it's easier to visualize the amount of twist. Okay, so if that's my rod or whatever, and just pretend it's a circle, right? And that's called point A, and that's called point B. And at point B, it's rotated this way by this amount. Okay, do you see how it's rotated like clockwise, for example? So if I draw this, okay, my rod has twisted from A to B, so we call that phi is a twist from A to B, so much, right? Okay, and if I draw like a line that cuts perpendicular to the top there at A, and do the same thing at B, okay, that's how much that's how much twist there is from A to B. Does that make sense? So that's like rotational displacement, right? So this is in radians. So what you'll find out later in this workshop is that radians, if you think about it, are actually unitless, whereas degrees actually have a unit. Okay, so I'll tell you what that means in a bit, right? But for us is like how we're taught in school, right? It's easier to visualize what degrees are, right? If I say 30 degrees or if I say 90 degrees, you can probably visualize that a lot easier than if I said 0.01 radians. Do you know what I'm saying? Okay, but radians is actually the most pure mathematical output. You'll see. Okay, so you want to convert everything in terms of radians, because degrees actually have an inherent unit, right? Okay, so I'm going to show you the formula for twist, and it just looks like this. Okay, so the amount of rotational displacement or twist is T, which is the torque, multiplied by the length. Okay, so on this rod, that's the length of the rod that's being rotated, over the shear modulus times the polar moment of inertia. Okay, So, yeah, it might look like quite a few things. You might recognize in week 4 we did like axial elongation and, or the amount of like elongation basically, right? That formula was PL on EA, for example, for a discrete. So for example, if you have a column and there's a force that's compressing it, how much is your column gonna shorten, right? That would be the formula which you would use, right? So you can see, again, analogies, right? P is like the force, whereas now we're dealing with T, which is the torque. L is that length. Instead of E, the elastic modulus, we're using the shear modulus, okay? And then we're using J instead of E, which is the cross-sectional area, right? So that was week 4. Okay. Okay, so similar to week 4, sometimes you're going to have discrete changes in your in your like rod, and sometimes you're going to have continuous changes, right? I actually drew this wrong. Give me one sec. I'm going to fix this up in my notes later. But okay, basically here's how I want you to think about it, right? So we've got a fixed end and a fixed end, which are just reactions, right? And therefore, if both these torques are going, so if I'm looking with my eye at that shaft that way, these torques are going clockwise, right? Yeah. And therefore, the reactions have to counterbalance it, so the whole system's in equilibrium. So the reactions are going counterclockwise, okay? Oh no, I drew it right the first time. What am I doing? Sorry. This should be clockwise. This should be clockwise. Okay, my bad. These should be counterclockwise. Okay, I had it corrected in my notes. Okay, so what I'm trying to tell you is if you think about a torque moment diagram, right, and I map it going left to right, whenever you have a clockwise moment, it actually brings you up in the torque moment diagram, right? So that jumps up. And then whenever you have a counterclockwise one, it goes down, okay? So you might think this is a little bit unintuitive and different to the direction of shear force, right, V. But it's actually the same as if you had point moments on a beam. So what I mean by that is just imagine you've got a simply supported beam, and instead of point torques, right, which is how I've drawn it there, if you instead have a clockwise moment on a beam like this, sorry, that one's the same way. So this is going clockwise and this is going counterclockwise, right, on the beam. A clockwise point moment actually gives you a positive, it makes you jump upwards in the bending moment diagram, if that makes sense. Okay. So if I was to map the bending moment diagram, pretending that treating the upwards direction as positive, then actually a clockwise moment brings you up and a negative one brings you down like this, okay? I don't know if I drew that very well, but does that make sense? Okay. So we're using the exact same convention as if we had a point bending moment when we're doing torsional moments, okay? So, yeah, if you have discrete changes, for example, if over here you've got a smaller cross-sectional area, and then over here you get a bigger cross-sectional area, then you basically have to split this up. So you would do the first part plus the second part. All right? Like that plus that. And then the thing that would change is J and probably L and probably T. Okay? So yeah, just look at the things that change between this portion and this portion, okay? Another thing that might change, another type of change is continuous change, okay? So, for example, here to here, we've got a bigger cross-section to the right, on the right-hand side than we do on the left-hand side, okay? So what actually changes is J, because remember J is a function of your radius, right? And if your radius is expanding, you can find that in terms of X, like as a function of X as you travel along this beam. Do you know what I'm saying? So you can like solve the torque based on integration. Oh, sorry, you can solve the twist based on integration. So that's like a continuous change, right? Okay, anyone have any questions about how this formula works? This should be pretty similar to what you saw in week 4. That's what I'm trying to tell you. For axial forces and stuff, right? And then the axial elongation and compression or whatever, or shortening. Okay, so essentially there's going to be 2 types of problems. The first one that you'll see is statically determinate, where you know what the reaction is going to be. And the other type is statically indeterminate, right? Where you use compatibility of twisting at the boundaries to give you an answer. Okay, so I'm going to show you 3 questions today. The first one I'm going to show you is going to be statically determinate. So here we've got a rod that's cantilevering against this wall, and there's 2 parts to it. The first one's made of aluminium, and the second part's made of steel. The aluminium bit's 75 mil long, and the steel one's 100 mil long. Okay. Okay. The sections are 6 mil in diameter. Okay, so from here to here, the diameter is 6 mil. Calculate the torque, this is part A, calculate the torque in which the aluminium section first reaches yield, and the aluminium has a material property where it yields at 100 MPa. Okay, so we're focusing on this part of the shaft, okay? Okay, so let me show you something, right? So if I was to draw the torque moment diagram, right? Oh, sorry. Let's do the free body diagram first, right? So this is what's physically happening. Okay, that's steel. This is aluminium. And we're applying a clockwise torque to it, okay? The reaction here at the wall has to counterbalance it because the system has to be in equilibrium, right? So, if we draw our torsion diagram, right, or torque diagram, the entire thing, so if it's counterclockwise, it goes down, right? The entire thing has a fixed amount of torque, right? The entire thing. So, we're trying to work that out, okay? What we're concerned about is some section. So let's call that section 1 to 1. So this is section 1 to 1. This is aluminium, and the shear stress distribution looks like this, right? Okay. And first, for the so the outer edge is the first part that reaches yield because, as I mentioned before with my weird analogy, right? The outer skin part experiences the most shear stress, right? When you're putting this whole thing into torsion, right? That's the torsion that you're putting. So that shear stress, right? We know that value has to be 100 MPa because that's the max it can experience before it yields, right? Okay, so we know the diameter is 6 mil. Therefore, the radius has to be 3 mil, and the max shear stress before it yields is 100 MPa. So if we rearrange this equation, so this is the formula that I gave you earlier. We want to solve for t, right? And also rho becomes c because we're only interested in the outermost point, right? If we rearrange this whole thing to solve for t, right, on the left-hand side, we get this. And if we were to elaborate on this, right, tau max is 100 MPa. J has a formula for a solid rod, and it's pi on 2, c to the power of 4. We know what c is. It's 3. It's also 3 down here. So this gives us 4,241 Newton millimeters, okay? So everything's in newtons, millimeters, and MPa. Okay, and then the next part of this question says, for an applied torque of 3,600 Newton millimeters, they wrote the wrong thing in the question. Calculate the max shear stress on the rod and the angle of twist in the 100 millimeters lengths of steel rod, right? Okay, so there's kind of it's kind of funny because there's two subparts to this, right? There's BI and there's BII. Okay, so for all of question B, we know that the torque is 3,600 now that we care about. All right. So irrespective of what we just calculated in part A, we know what we actually are provided in the question is 3,600 now. Now we have to find part I, the max shear stress in the steel rod, based on this new applied torque, and we also have to find the angle of twist in the 100 millimeters length of steel rod, okay? So based on this amount of torque, we use these two formulas, that's what I'm trying to say, okay? So we can plug in 3,600 for T, and we can plug in C is equal to 3 millimeters. J is pi on 2 C to the power of 4, where C is 3 millimeters, right? Giving us 84.89 MPa, okay? So that's the max shear stress that's being experienced by the entire system. Sorry, yes, basically, by the entire system, given this amount of torque instead, okay? Okay, and then the second part is what's the twist in just the steel? Okay, so before I need to give you guys a bit more context, okay? So again, I know we have a cylindrical rod, but it's very hard to demonstrate what's going on if I just show you it as a circular cross-section. So instead, I'm going to show you it in terms of a square, okay? Just trust me, all right? Okay, so you've got a square like this, a square section, and this part's aluminium and this part's steel, okay? Let's talk about these in terms of points A, B, and C, okay? The idea is the cross-section at A has zero twist because this is fixed, right? So we know that the twist, we know the twist at A is 0, right? That's like our starting point, okay? If we apply a torque, was it clockwise? No, it's counterclockwise, isn't it? If we apply a torque, at B, it might rotate this much, and at C, I'm just going to exaggerate it, it might rotate this much. Yeah? So drawing the lines that connect it, do you see how it twists more and more from A to B and then B to C? Okay. So, if we call these twists, right? Basically what I'm trying to say is twisting, like this formula for twists, right, actually needs 2 points of reference, right? You need your starting point and your finishing point, and then between those 2 points, how much is it twisted? That's what I'm trying to say, right? So if you're considering the amount the angles change from A to B versus B to C, right? You'd have to notate it like this, and the overall twist from along the shaft, you basically add them together, so you can get the twist from A to C. Okay, that's if you're concerned about getting the twist from A to C, right? Like how much is that cross-section rotated from here to here? But actually how the question is worded is we only care about the steel portion, okay? What's the relative twist B to C? That's what the question's asking from us. We only care about how much does it change from here to here. Does that make sense? Okay, so that's what we're gonna do in the question, okay? So we're only concerned about the steel portion. Like we don't actually care about how much the aluminium bit is twisted. because we've only got 100 mil of steel. We have the same torque as we were given in the question. The shear modulus of steel is 80 times 10 to the 3. And J is 127.23. Okay, so where did I get that from? I basically just got that, and that's a simplified version of that. Okay, giving us 0.0354, and remember this is in radians. Okay, so whenever we plug things in this calculator, it becomes unitless. Whenever we plug this into this formula, it becomes unitless, right? It's in radians. Okay. All right. Any questions about that? Nope. Okay. I've got another question. So now we basically have this rod and it's floating, right? Just pretend it's suspended in the air for whatever reason. And one way you can think of the forces, at least at the very start, is just pretend these are fixed. You'll see later when we're talking about the twist, this isn't actually the case, but think of it as fixed for now, okay? Think of this like a rod that has two fixed ends, and there's two point torques that are applied, and then two counterbalancing reactions, okay? But you're told exactly what these are. You're told this is 4 kilonewton meters, 3, 6, and 5. So basically the sum of the torques is 0. The whole system's in equilibrium, right? Okay? So think of it like that for now, and then I'll explain why it's not quite like that, okay? But in terms of how we map out the torque diagram, this is actually a completely fine model to think about, okay? So we want to sketch the torque diagram first, okay? So how does that look? Remember, if you have a clockwise torque looking this way, if you have a clockwise torque, it's going to give you a positive jump in your torque moment diagram. So that jumps up to 4, okay? And when you reach 1 meter, it jumps down by 3 because there's a counterclockwise torque. So that jumps to 1. And then if you further torque it 6, right, it brings you down here to -5. And then at the very end, it all reaches equilibrium because there's a restoring 5 kilonewton meter torque that's going clockwise, right? So that's the torque moment diagram, okay? And we're basically concerned about this part because this has the max torque, right? So in terms of like a material yielding, right? So pretend this like whiteboard marker is made of steel or whatever, and pretend it's really, really soft for some reason. If I turn it, I don't care if I turn it clockwise or counterclockwise, it's going to yield at the same point, right? It's just based on the magnitude, not which direction I'm turning it, okay? So if you get a negative magnitude, it's still going to cause it to yield in shear, right? Does that make sense? Okay. We're told in the question, find the minimum value for the external diameter, okay, if the shear stress must not exceed 85 MPa, okay? So we're told the max shear has to be, shear stress rather, has to be 85 MPa. And we know that the max torque in the overall system was 5 kilonewton meters, which is this. And so we want everything in terms of these units, right? We want MPa, newtons, and millimeters, okay? So we're going to convert kilonewton meters to newton millimeters. And the way we do that is we multiply by 10 to the 6. Okay? So that gives you how much torque we need to plug in. Okay? Here's our formula. And we want to work out C. We want to work out the radius, right, which corresponds to this amount of torque and shear stress, right? And what we can do is we can simplify this because we know for a solid rod that that the expression we have for polar moment of inertia is already a function of C. And so we can simplify it. So if I get rid of the c at the top and then punch this down to 3, right, we get this expression now. So equating this left-hand side with the right-hand side equations, we can rearrange for c, and it results in this cube root, right? So we can find what the radius is based on this, okay? So the max torque is 5 times 10 to the 6, and the max shear stress that is allowed is 85. Therefore, when we punch this into the calculator, we get 33.46 as a radius, right? But the question is asking for the diameter, and we know the diameter is twice the radius, so that gives us 66.91 millimeters, okay? So, but for the purposes of continuing to the next part of the question, I would recommend that you stick with radius, because all the formula is going to be in terms of radius. It's going to be easier than doing it in terms of diameter, right? Okay. So the last part of the question, for a shaft with this minimum diameter, calculate the relative rotation of sections A to D, and then we're given the shear stress. Okay, so here's where my my analogy that you can consider this as fixed breaks apart, right? So you can't consider this fixed anymore. You can only consider it fixed for the purposes of calculating the torque equilibrium, right, within like a stick. So the idea is that for this floating rod, right, for this floating rod, again, it's easier to visualize the twist if I do it as a square rather than as a circle. If I'm applying these kind of moments to it, right, and this is the reference point A. If I rotate it like that, sorry, it's the twist is going the other way. So it goes like that, and then it goes even more like that, and then maybe there's a bit of a restoring torque, like there. Okay. You get what I'm trying to draw here? The idea is that at points A, B, C, D, okay, where the cross sections look like this, like this, like this, like this, we can only consider one part as like the reference, right? So A, let's just pretend the torque starts at 0. The twist starts at 0 here. It can rotate counterclockwise, and then counterclockwise again, and then clockwise again. But it doesn't necessarily have to result in 0 twist. Okay, so this is the case if you've got a floating rod. Okay, nothing's there to anchor it in place. If I had a fixed end, we know the twist at both of these would be 0. Okay, but since we've got this floating rod, the twist doesn't necessarily have to result in the equilibrium. Okay, but the forces do. Does that make sense? The forces in anything, even if it's floating or not, like the internal forces have to be in equilibrium. Otherwise, it will just be in perpetual motion. Do you know what I'm saying? For statics and for civil engineering, we're focusing on equilibrium. Okay. So, with all that said, basically, we want to do this, right? We want the twist from A to B, we want the twist from B to C, we want the twist from C to D, okay? And in order to work out the twist from A to D, we just have to add all those things together. But what I'm trying to tell you is from A to D is not necessarily equal to 0, okay? So when you've got two fixed ends, we know that their relative twist from each other has to be 0. So that is true, like that is equal. But for our particular case, we just add these individual components together, okay? So that's our approach. So the parts that stay the same are the radius, right? The radius is 33.46 as we worked out before, and the shear stress, the shear modulus is 85 times 10 to the 3. What does change between these different parts of your shaft are the lengths between, like the lengths and the torque. Okay, so again, looking at the torque moment diagram, right? This is easiest to see here. We've got 4 kilonewton meters from A to B. We've got 1 kilonewton meter from B to C, and then we've got -5 from C to D. And then also the lengths are different, right? So these are in meters, but they're 1 meter and 1.5 meters. So for that first part from A to B, we have a torque of 4 times 10 to the 6 Newton millimeters, and we have 1,000 millimeters, okay? And then the second part is 1 and 1,500, and then the third part is -5, note this negative here, which corresponds to the -5, right? And then it's 1,000 long, okay? So that one will give you a negative twist value, okay? Okay, when you punch all of this in the calculator, you just simply get 0.003 radians, okay? So that's the difference in twist from point A to D. So along the entire shaft and all those various, what am I trying to say? All those various point loads corresponds to this in terms of a twist in the end, okay? All right, any questions? Again, I think it's pretty easy, right? We're up to our last question, and we're not even 1 hour in. Okay. So I'll just show you this last one. Okay. So I'll tell you about part A, and then when we get to part B, I'll tell you why it's a bit funny. Okay. So we basically have a fixed end. Okay, which in this course is actually not that bad. Oh, sorry, not in this course. What I should say is, what did I just click? What I mean is, in this topic, having a statically indeterminate system is actually not that bad. Okay, you can work it out relatively easily. So basically, you have a bar, and from A to B it has a large cross section. It has a diameter of 40. And from B to C, it has a diameter of 20, okay? The bar is fixed at each end so that the rotations at section A and C are 0, okay? So we've got 0 twist here, and we have 0 twist here. An external torque is applied, this one, at section B, and causes the section B to rotate through an angle of 1 degree. Find the maximum resulting shear stress in the bar and take this as the shear modulus, okay? So the first thing we had to do is we had to convert our degrees into radians, right? So if you see degrees in the question, that should be an instant red flag, and you should change it straight away to radians, okay? All right, guys, I've got a pop quiz for you. Which way do I multiply in order to convert degrees to radians? The first way or the second way? Because this is something that I got confused about a lot when I was an undergrad, but I found a very good trick, okay? And it's to think of it in terms that degrees have a unit, but radians don't, okay? So if you think of it like this, right? I put 1 degrees, right, with the circle. If I put 180 degrees, we know these units actually have to cancel out. So it has to be this first one, right? Because otherwise you'd have degrees squared, right? Because if I multiply 1 degrees by pi over 180 degrees, yeah, the degrees cancel out on the top and the bottom of the fraction in terms of their units. That's what I mean by degrees actually have units, you know what I'm saying? Whereas radians don't. Radians are unitless, okay? Oops, I just rubbed the microphone. Sorry to everyone who just is watching this in the recording. Okay, so that gives us 0.0175 radians, okay? You can think of the fraction at the top here as saying radians if you want, but radians, again, the unit list, so you don't really have to. Do you know what I'm saying? Okay, so basically now we can derive an expression for the change in twist from A to B. Okay, so we know that. Okay, so we know the twist at A is 0, and the twist at C is 0, and therefore the twist at B, which we just calculated as 0.0175 and is told to us in the question, right? Therefore the change in twist from A to B has to be that, right? Because it had a starting point of 0. So we just chuck this into our fraction and then set it to be equal to all this. Okay. We know the shear modulus already, and we know an expression for the solid rod polar moment inertia, right? So we can replace C with 20, because this is a diameter of 40, right? So if we go half to find the radius, we get 20. We know the length between A to B is 700. Okay, and the only thing we don't know is TA, but we can rearrange and solve for TA. Okay, so that's the amount of torque at the support. Okay, so what does this look like on a torque moment diagram, right? So if I draw a free body diagram first, right? Again, you don't have to do all this like extra detail like I'm doing right now. It's just I'm just trying to explain it better. Okay. If I did a torque moment diagram, I guess firstly what's important to explain is from this diagram, we know that here we had a counterclockwise torque, right? And we know that at both these reactions, let's call it TA and TC, we know both these reactions have to equal the torque that we applied. I'll give you an example, right? So if we think of this like free body diagram on a beam, and there's a point load, let's say here, we know that the shear force, right, of this system, of this particular system, would look like this, right? Oh, sorry. It would be lower. It would have a lower reaction at A and a bigger reaction at B because it's more leaning towards the B. And for the system to be in equilibrium, this first area has to equal this second area, right? Yeah. So that's for shear force. For torsion, it's the exact same thing. So we've got a clockwise moment, which brings us up a bit. And then we have a certain drop. And then we have, yeah, it basically just looks like the same shape as we had before, right? But how much it jumps up is by the reaction, down by the amount that we've torqued in the middle, and then up by that reaction at C, okay? Does that make sense? So what we just worked out was TA. So we worked out the fixed supports torsion reaction, okay? Which was this, okay? So that right there is 5.3, 3 times 10 to the 6 Newton millimeters, okay? That level here. And we can use compatibility to work out the other reaction, because remember, this is statically indeterminate, right? So we don't know what this is, okay? So we know that it has to start and end at 0, right? The twist. So this has to be 0, and then this has to be 0 on either end, right? And so the twist, the twist from A to C, the twist from A to C has to be the twist from A to B plus the twist from B to C. And the whole thing has to have a net change in 0, because we know it goes from fixed end to fixed end, right? So the 0 twist as a net, right? So we can set up this equation, and TA, we've worked out, is 5.33 times 10 to the 6. We've worked out all this other stuff. The radius for the big part, for the big cross-section, was 20. So that's a radius of 20. And then there's a radius of 10 for the small part. And we know that this is 700 mil and this is 300 mil, okay? So this one is a twist that's going, which way is it going? It goes counterclockwise and then it twists back clockwise, right? And so we can work out TC. So we can solve for TC, giving us 7.77 times 10 to the 5. I don't have my units here, but it's Newton millimeters, okay? So that is basically here. That's negative 7.77 times 10 to the 5. Okay? And that's the same as TC. Does that make sense? Okay. So, yeah, basically, it's kind of weird. Oh, right. I see what's going on. Oh, okay. I didn't actually answer this. Okay. I'll tell you how to answer that later, but I basically want to find the resulting maximum shear stress in the bar. Okay. So, so basically, at segment AB, we have this much torque, right? And then at section BC, we have this much torque. So it's asking you what's the shear stress here, and then what's the shear stress here, right? So we're going to call that shear stress from A to B, and we'll call this shear stress from B to C. Okay. So we're going to plug in our values that we know, which are 5.33 times 10 to the 5, 20, giving us 42.39. That's for segment A to B. And for segment B to C, we plug in the other value that we know for torque, and we have a smaller radius, right? Giving us a different number, 49.45 MPa. So the max stress in the bar is just whichever one gives you a higher number, right? Which is 49.45, okay? Okay, so the other part, which I haven't actually got the solutions prepared for, right, is saying that this bar is subject to an external torque applied at D, which is midway between A to C, okay? The resulting rotation of the section is at B is again 1 degrees. Find the rotation of the section at D and hence the magnitude of the applied torque. Okay, so let me draw this very nicely. So here's our free body diagram. Oops. Here's one wall. Here's another wall. So the torque is now applied in the very middle. So this point we're going to call D. Here we'll call A. Here we'll call B. Here we'll call C. Again, yeah, the torque is applied here now. So it goes like that. T. We're going to have different reactions now, TA and TC. Right? Oh, let me turn that back on, sorry. Yeah, go on. And in terms of dimensions, D is in the midpoint, right? So that's at 500. This is 200 apart. And this is 300 apart, okay? So the whole thing's 1 meter long. And what the question is telling us is that the twist at B is still 1 degrees, or in other words, 0.0175 radians. Okay. But now the torque is applied here, okay? So the first thing we have to do is basically, we have to draw the torque moment diagram. Okay. And you can see this left shape has to equal the right shape, okay? So it's kind of a funny scenario, right? TA and TC have to be balanced because this torque is applied in the middle. It's like it's like, imagine you had a point load in the middle, right, of two supports. All right. These reactions have to be balanced, right? Such that the shear force looks like that. I'll give you another example, right? If you have a moment here and a moment there, if you apply a point moment in the middle of this, right, the bending moment diagram, rather than the shear force diagram, this is for a beam, right, also looks like that, basically, right? So, oh, sorry, other way. Yeah. So we're doing the same thing. It's just this, to be in equilibrium, this area has to equal this area. That's what I'm trying to say, okay? So we basically know that TA is equal to TC, which is equal to T on 2, okay? So the next thing you got to do is basically figure out the twist. So the twist from here to here is probably easiest to work out. So we know that the twist here is 0, right? And then the twist at B is that. So the twist from BC is that. Oh, sorry. Is that right? Yeah, BC, yeah. Let's make it negative. And it's equal to TC times L times GJ. And we're working out TC basically, that's what we care about. We know this length is 300 mil. We know G is 85 times 10 to the 3. And we know J is pi on 2 c to the power of 4. The radius is 10 for the smaller diameter thing. So we've basically just, we're just working out what TC is, okay? TC, I had to get my calculator out. One sec. Sorry guys. TC is 85 times 10 to the 3 times pi on 2 times 10 to the 4 divided by 300. TC is 7.79, let's say, times 10 to the 5 Newton millimeters, okay? And we know, if I just erase all this other yapping, we know TA and TC are both equal to this, right? Okay. And basically the rest of the question is just asking you find the rotation at segment D. Okay. So if that's the torque moment diagram that we've now solved, to find the twist, we can go here. The twist is 0, and we want to go to D. Okay, so we want to find the twist from A to D. The twist from A to D, we only have to consider this portion of the bar, and so that's T of A multiplied by C. Sorry, wrong one. Times L over G times J. Okay, so L is 500. T is 7.79. This one's negative. Times 10 to the 5. And then G is 85 times 10 to the 3. J is pi on 2 times, this one has a radius of 20 to the power of 4. So if I was to punch this onto my calculator, assuming I typed this correctly on my calculator, the answer is 0.0018. So that's the amount of radians that it's twisted from A to D, okay? If the torque was applied at D, okay? Does that make sense? So this part, right, part B, because you've applied the torque instead of at B, if you've applied it at D, which is over here, you've changed how much reaction is at A and how much is at B. Sorry, how much reaction is at A and how much is at C. Okay, well, you basically changed that dynamic, so you have to recalculate those reactions, and then you find the twist accordingly. Okay, so that's the last question I had ready for you guys. But we're pretty much done. That's it. So, do you guys have any questions about how that works? No? Is it all right? Easy? Yeah, I think this topic's not too bad. There's only 2 formulas, right? There's only so much you can fuck it up by. Do you know what I mean? So, good luck, and I'll see you next week where we've also got another breezy topic, so should be all right. Okay, see ya.